Everyone. So today I wanted to show you a tutorial on how to analyze a regression output whenever we're using the analysis tool pack in Excel. And if you're ever using Minitab or a similar statistics program to analyze a regression output, this should be extremely similar. So I'm just going to briefly touch on how to download it. So I'll put a link in the description for the timestamp so you can just jump ahead right to the analysis of it. But really, if you have Windows, you're going to follow these instructions right here. It should be pretty straightforward. For Mac, you follow these instructions. And then simply what we're going to do when we use the analysis tool pack for regression is that we're going to click on the data tab right here. On the far right, you're going to see we have a data analysis right here. So we're going to click the data analysis. We have a regression section. We're going to click regression. And then you can see that depending on which set of data that I'm interested in, I'm going to highlight a Y range, then click here, highlight an X range, and then just click OK. So I actually already did that for you. I just wanted to show you how to do it so we can jump to the analysis. So first what we're going to look at is the analysis output for this set of data right here. And then we're going to go in, which you can see is simple regression because we're using one X to predict one Y. Whereas here is multiple regression where we're using more than one X to predict one Y. So let's talk about the simple regression output first. So you can see right here, it's a bunch of information that you're given to start off with. So one thing I want to point out is that I have all of these text boxes right here. This is all stuff that I've typed to sort of help you kind of give a guideline on what means what in this. All the information that you actually receive from clicking OK for the regression analysis is all of this information right here under summary output. So you can see that there's a lot of different things we can analyze whenever we're dealing with a regression analysis. Whenever we have a line of best fit that's attempting to predict Y given some X. So I just wanted to hit the highlights, kind of show you some very key formulas. I'm not going to go over every single line item in this output, but it's going to hit a lot of the ones that you may see on your exams that may be important if you're doing certain data analyses. So one thing I want to point out is that this ANOVA table right here, pretty much everything that you need to know about that is going to be covered in this video I made right here, the Business Lab at Home ANOVA table overview. So definitely go to the channel and check that out if you're kind of wondering what each of these represent and kind of how the relationships work between each of these values, because that's all covered right there. But to start off with, just kind of from the top, some of the main information you're going to see is something dealing with your multiple R. That's simply known as your correlation coefficient. You might just see it as R alone, and that's a number between -1 and +1, and it basically gives you a good idea of how strongly fitted the data in your data analysis is fitted to your line of best fit. So that's how you find that value. If you're kind of wondering more how to interpret that and what that means, I also have another video right here, the correlation coefficient overview video, that you can look at on the channel, but that is how you identify it. It's simply listed right here next to multiple R. Now, R squared is just literally the R right here squared. So it also gives you a pretty good idea about the relationship between X and Y, but where the simple R, the correlation coefficient, tells you not only the strength of the data to the line, but also the direction the line goes, whether or not it's a positive or a negative relationship. R squared really kind of focuses more on just the relationship between X and Y, not positive or negative, but how strongly fitted that data is to the line. So that's how you interpret that right there. There are two other formulas that I've seen in my classes before that you might want to be able to know just so you can back into this number if you don't, if it's blanked out and you have a lot of information, you have to sort of fill in the blanks for what's provided based on the relationship between all these values. R squared is literally just this multiple R squared. So if you have your multiple R, you can simply solve for R squared by squaring it. Another way you can solve for that is that if you take 1 minus your SS residual right here, so in this case it would be 35.63 roundabout, divided by your total sum of squares, your total SS, which is going to be the total, the 55.2 right here, the total SS. Take 1 minus the SS residual divided by the total SS, that's going to give you this value right here. So lots of different ways you can use to solve for these numbers right here. Like the standard error, for example, is just the square root of your MS residual. So if you took the square root of this, it will give you this number right here. So lots of different relationships between these numbers that you can check out. What I think is one of the most key things to look at is that all of this information down here, especially under this coefficient section. So remember, when we're dealing with a regression analysis, what we have is this standard format line of best fit formula where it's y hat equals b naught plus b1 times x. And we also have have a regression overview video that we cover in another video in Business Lab at Home, so look at that if you're just kind of wondering the concept of it. But once you've sort of had that established, you can actually construct what your line of best fit is simply given this information right here. So a coefficient is really in that formula going to be a constant value that you plug in. So for instance, the intercept coefficient, we know that b naught in your y hat equals b naught plus b1x formula. The b naught is your y-intercept. So this intercept is referring to that y-intercept, and it's letting you know that your b naught, the coefficient for the intercept, is about 27.53. So you can see that the intercept is b naught, which equals 27.53. The b1, on the other hand, relates to the specific x values that you would be plugging in. So the b1 coefficient, which you multiply by some input x, just some x that you come up with to predict your y hat, that's going to be around about negative 0.43. So if I were to create my line of best fit formula just from this output, it would be y hat equals 27.53 minus 0.43 times x, whatever x is. So you can create your line of best fit formula from these coefficients right here. Apart from that, it might be important to note that your t-test statistics right here, just again, if you're kind of given some information was blank, some information was provided, and you kind of had to figure out how you got that information, the way they come up with these two numbers is that they took the coefficient for that row and they divided it by the standard error. And you can even see, it's hard to divide that in your head, but 27.5 divided by about 11 makes sense that that's maybe about 2.5, but those numbers do check out if you were to do them on your own. So that's how you find your t-test statistics. As far as your p-values are concerned, let's look at the explanation on the right over here to sort of analyze that. So one important thing to note is that the standard hypothesis setup for simple regression is as follows. H0, your null hypothesis, is that B1 equals 0, and that HA, your alternative hypothesis, is that B1 does not equal 0. So here's what that means. So it's important to first interpret what each of those mean so that once you accept or reject them, you know kind of how that actually correlates to the real purpose of what's going on in the problem. So HO, that B1 right there, normally you might see that as kind of a curly Q little b. I'm not sure what the exact variable name is for it, but that directly correlates to your B1 right here in your line of best fit formula. So let's think. If B1 equals 0, that would mean that instead of 0.43 right here, it would be 0. So if I were to plug in some x, like I'm trying to use x to give me an idea of what y hat would be, and hopefully that would be a meaningful relationship, otherwise this isn't a very good model to use. If this was 0 right here and I plug in some x, no matter what x I plug in, it's immediately multiplied by 0, and my y hat's just going to be 27.53 every time. So it'll be 27.53 minus something times 0, which is just 0. So you can see if that's the case and we accept this hypothesis, that means that B1 is not a very useful predictor in helping me determine my y hat, because any x I plug in is just immediately multiplied by 0, and it doesn't tell me anything about what y hat might be. So it wouldn't be very useful. Whereas HA is where it does not equal 0. So if you were to accept that hypothesis, that would be saying that B1 is fairly useful, at least to some degree, in helping to determine your y hat. So remember that you accept or reject your hypothesis based on your p-value versus your alpha, which is your level of significance. That should be given to you by, let's see, if you're working through a statistics problem, that will either be provided to you. If it's not, the general rule of thumb seems to be that you just say it's 0.05, and that's going to be your level of significance. So simply, you can see that each of these values, the intercept and the x variable, have their own p-values tied to those variables. So those p-values you should compare to an alpha. And if the p-value is lower than your alpha, that means that you're going to reject HO and claim that that would be useful in helping you predict your y hat. So for instance, let's say that we had an alpha of 0.05, and I'm trying to decide whether or not this B1 is useful in helping me predict my predict my y hat. Well, I look at my p-value right here, and at 0.05 alpha, this is actually greater than my alpha. And when my p-value is greater than my alpha, I accept HO. Well, HO means that that's not very useful in helping me predict my information. So what I would conclude in this situation is that X isn't super useful in helping me predict my Y hat. At least it's not as useful as perhaps another X variable that we could use instead of that. So that's how you interpret that. And now, real quick, let's segue into the multiple regression output right here. You're going to see it's nearly identical, except we have multiple rows for each set of data where we have this is our y variable, this is our x1, this is our x2. So if I were to create, first of all, my line of best fit formula based on my coefficient information here, you would see that the intercept is 25, rounded, 25.08 is B0. My B1 is negative 0.56, and my B2 is 0.50. So if I were to create my line of best fit formula, I would say that y hat equals 25.08, which is B0, minus 0.56 x1 plus 0.50 x2. And so I'm using multiple x variables to help me predict my y hat to come up with what I think y would be given those x's. So the same situation applies where we can analyze each p-value to decide whether or not that is a useful predictor. So remember, if the p-value is lower than my alpha, I reject HO and say that that would be useful because I'm rejecting the notion that it would not be useful. So really, the lower my p-value is, the more useful it is in helping me predict it. So what you can do is look at these p-values right here between your x1 and x2 and ask yourself which one is going to be a little bit more useful in helping you predict it. Well, in this case, it would be the x variable 1 right here because the p-value is much lower. Now, compared to likely level of significance, maybe neither one is all that great at predicting it because odds are you want it to be as close to 0 as possible, your p-value. So it's lower and lower, meaning it's a stronger connection between that predictor variable and your y-hat. But if you were to decide, okay, maybe I should eliminate one of these two, especially if you have multiple outputs, like for instance, if I'm wanting to perhaps predict the price of a house given the square footage, the number of bedrooms, the number of bathrooms, whether or not it has a garage, if it's in a certain school zone, just all the different things that can compile into the price of a house, some things don't connect to it as much as other things. So if you want to come up with your set of your best predictors, what you would do is simply run the data analysis again, but exclude whichever x variable had the higher p-values, so on and so forth. So you can see that, this is very similar. I think the notes I have right here pretty much cleanly translate over into the multiple regression section. It's just important to keep in mind that as you have multiple regression, you have more rows of information right here dealing with your x variables. Thus, you can create your even larger line of best fit formula and you'll be good to go. So I hope that clears some information up if you're ever having to analyze your analysis tool pack. Again, this doesn't cover every single line item that you might have to worry about, but it hits the highlights, and I think it covers a lot of what you might see in your introductory statistics classes. So thank you so much for watching, and I hope that helped.